Welcome to the introduction of our series, The Grand Beginning. Our universe is vast and mysterious, filled with billions of galaxies, each containing billions of stars. The prevailing theory is the Big Bang. It suggests the universe originated from an extremely hot, dense state. It expanded and cooled, forming everything we see today. About 13.8 billion years ago, the universe began to expand rapidly. The Big Bang theory is supported by evidence like cosmic microwave background radiation and redshift in galaxies. In Section 2, we delve into the early universe, a hot, dense soup. In the first few minutes after the Big Bang, the universe was like a cosmic soup of elementary particles. The temperatures were so high that atoms couldn't form. Protons and neutrons collided at incredible speeds. However, as the universe expanded and cooled, these particles began to combine. Around 380,000 years after the Big Bang, the universe had cooled enough for atoms to form. Electrons combined with protons and neutrons, creating the first atoms of hydrogen and helium. These atoms were still too hot to emit light. The universe was a dark, opaque fog. This period, known as the Dark Ages, lasted for hundreds of millions of years. Gravity began to pull matter together, forming the seeds of future stars and galaxies. The Big Bang theory provides an elegant explanation for the abundance of hydrogen and helium in the universe. In our final section, we explore From Particles to Galaxies, Gravity's Masterpiece. Over vast stretches of time, gravity played a crucial role in shaping the universe. The tiny fluctuations in the density of matter in the early universe grew larger under gravity's influence. Denser regions attracted more matter, becoming even denser. These regions eventually collapsed under their own gravity, giving birth to the first stars. These early stars were massive and short-lived. They burned brightly, fusing hydrogen and helium into heavier elements. When these stars exploded as supernovae, they scattered these heavier elements into space. These elements would eventually become the building blocks of planets and even life itself. Over billions of years, gravity continued to draw matter together, forming galaxies. Our own Milky Way galaxy is just one of billions of galaxies that populate the observable universe. These galaxies are not randomly scattered. They are arranged in vast cosmic structures like filaments and voids. Section 4. Echoes of the Big Bang. Evidence for the theory. The Big Bang theory is supported by several key pieces of evidence. One of the most compelling is the cosmic microwave background radiation, or CMB. The CMB is a faint afterglow of the Big Bang, a whisper of light from the early universe. It was discovered accidentally in 1964 by Arno Penzias and Robert Wilson. Another crucial piece of evidence is the redshift of distant galaxies. Redshift is the stretching of light waves as they travel through space. When astronomers observe distant galaxies, they notice that the light from these galaxies is redshifted. This redshift indicates that these galaxies are moving away from us. The farther away a galaxy is, the faster it appears to be moving away. This observation supports the idea that the universe is expanding. The Big Bang theory provides a natural explanation for both the CMB and the redshift of galaxies. Section 5. Dispelling misconceptions. The Big Bang was not an explosion. One common misconception is that it was an explosion in pre-existing space. However, it was the expansion of space itself. Imagine a balloon with dots on it. As you inflate the balloon, the dots move farther apart. The Big Bang happened everywhere at once. The universe has no center and no edge. It describes the evolution from a hot, dense state to now.